Okay, let's start. Maximize this. So good afternoon, everyone. Welcome to this webinar. The title of the webinar is Laser Testing of Single Event Effects and Case Studies. My name is Rez Mani, and I work for the company Allied Scientific Pro. I've given this webinar a number of times, and I should also say that the webinar is being recorded, and the recording will be sent to you within a few days. So I have received a number of comments and feedbacks from the audience in the previous webinars. And I would just like to say that basically this webinar has a bit of a educational nature. So we talk about the basics of the single event effect. And also I'd like to mention that we are not a research company. We build SCE systems, and the case studies that I will present is also has been done on chips that whose SCE behavior has already been known in the literature, and papers have been published on them. So there's nothing new in them. So we just use these chips to verify the performance or validate the performance of our systems. So I hope that this part is clear. So let's just move on to the outline of the talk. So I'll talk about what is single event effect and the types of single event effect, whether they're destructive or non-destructive, or you can also say hard errors, soft errors. Then what is the need for testing of satellite instruments for SCE? Then I'll talk a little bit about the radiation method for SCE, which is the standard method of testing. It's a standard method of testing. Could you please put your microphones on mute? Yeah, great, thank you. So then I would get into the pulse laser testing for SCE and discuss the single photon absorption and two photon absorption methods. And then I would discuss basically I would compare the pros and cons of TPA versus SPA. Also, I would just introduce the Allied Scientific Pro's pulse laser SCE testing system. We have a lab here where one can come and do testing. You could rent the lab time and use the equipment, or you can also purchase our equipment. Then a little bit about the wide bandgap semiconductor SCE testing, gallium nitride, silicon carbide, gallium arsenide. And then I'll get into these case studies for some components that we have tested, the SRAM HM6504 and the OPAM LM124. So as I said, the behavior of these chips as far as C is concerned or SCE is concerned is available in the literature, and we just use these to validate our system. And then I'll talk about the commercial SCE systems that we produce. Okay, next. So what is a single event effect SCE? So this happens when a charged or an uncharged particle passes through a circuit, strikes an electronic circuit, and it produces electron hole pair along its path that would disrupt operation or could destroy a circuit potentially. So you can see here the charged particle is passing and producing these electron hole pairs. And as we know, all the satellite instruments, they have many electronic devices on board, such as static and dynamic RAMs, microprocessor, logic gates, EEPROMs, power MOSFETs, ADC, DAC, and so on, and also components such as op-amps and flip-flops. And this operation of these devices could be disrupted by particle strike. So these circuits need to be tested prior to launch, and it should be observed whether they require radiation hardening and where are the sensitive spots on these circuits. So what are the sources of these charged particles in space? There are basically three sources. The first one could be cosmic rays. So for example, if there's a supernova explosion somewhere in another galaxy, it creates a lot of charged particles and it sends it towards our galaxy, and eventually it reaches the Earth. So basically, so this is the planet will be bombarded by protons and heavy ions, and satellite that is revolving around the planet could receive these heavy ions and protons. The second source would be the sun. Sun emits a huge flux of charged particles such as protons and heavy ions, alpha particles, and especially during solar flare, the flux of these particles would increase, and some of these charged particles are trapped in the Earth's magnetic field, and they form the Van Allen belt. So if a satellite is passing through that, will receive these particles. And finally, the secondary particles you can see in this picture, on the top picture. So let me, yeah, this is the pointer. So this primary particle could be a proton. When it hits the atmosphere, it could generate a cascade of secondary particles such as neutrons and the muons, neutrinos, and so on. So a satellite that is being launched or in the low orbit could also receive these particles. So what are the types of single event effect? We have two types, non-destructive and destructive. The non-destructive could be single event upset, SEU, single event transient, SET, single event latch up, SEL, and single event functional interrupt, SEFI. So for example, in this picture, you can see a charged particle is struck an SRAM, for example, and has switched the state of this cell from 0 to 1. And over here, another particle hits a logic gate, and it produces the transient pulse. And you can see that here, that's the set. And that propagates down the circuit, and somewhere along the line, it will flip the state of the cell from 1 to 0. So a set would cause a SEU. So these are some examples of non-destructive SE. And then you also have the destructive, which could be single event latch up. That's also another way. It could be destructive or non-destructive. So cell is part of both of these categories. And you can also have single event gate rupture, single event burnout. So I'll discuss each one of them in the next slide. So for the single event upset, we already talked about it in the previous slide. Single event transient, also temporary pulse traverses the circuit. We showed that. And what about latch up? The latch up always is accompanied by a large current flow, and the chip gets really hot and basically upset bits that may lead to disruption of circuit operation. So the circuit will not operate and gets very hot. So if, for example, it's A to D converter, it doesn't work, or if it is an SRAM, you cannot write on it anymore. It's just stuck there. So the only way to remove the problem would be to do a power recycle. So turn the power on and off and on, and that may fix the problem. So that is a single event latch up. For single event functional interrupt, it happens when the charged particle hits the control circuit, not the actually memory cells, but the control bits. And that would basically cause an interrupt in the circuit, and it's a malfunction. It doesn't work anymore. So you don't need to do a power recycle, and there is no heated chip, and there is no large current flow. You need just to reset the system, and it will go away. So that's a SEFI, which is different from the cell. And for the destructive, we have the single event burnout. You can see here the 120 volt DC to DC converter has been charged here. So, and it's just not functional anymore. It's destroyed completely when there is large energy strike of charged particles happens. It happens in that case. You can also have a latch up in case the current is too large. It could potentially damage the part. So even doing a power recycle would not solve the problem. We have tested this in our lab, and I'll show you in future slides when I get to the case studies. So that's a destructive latch up. And then the last one, single event gate rupture. It happens in MOSFETs, and this is when the gate area basically is shorted out due to strike of the particle, and basically there's a large current that flows between the source and the drain, and that would burn and destroy the circuit. Now, it's interesting to note that this is the only single event effect that cannot be produced with the visible and near IR lasers, the type of lasers that we use for SCE. And I need to explain why is that. So you can only produce this with the particles, but not with the visible near IR lasers. And the reason for that is that the gate material is usually made of insulator. So you need to ionize the gate insulator in order to get this effect. And you can do that with high energy particles, but the visible or near IR photons do not have that much energy to ionize the gate material, which is an insulator. So for this reason, you cannot get it unless you use a UV laser or an X-ray laser that has really high energy photon. And at the moment, we are not using those. So that's the reason you cannot get the SCGR with the optical method. Okay, next, what is the need for testing of satellite instrument prior to launch? So one has to find out all the sensitive nodes of a circuit before launching, so that this will not cause problem, obviously, in the space. And nothing can be done about that. For example, here you can see the SCU sensitivity of a SRAM cell has been plotted here, and the red areas are the ones that are very sensitive. The most sensitive, the yellow are less sensitive. So these kind of maps are very useful for the designers to see what they can do after doing the testing. They need to find out what they can do to maybe do some radiation hardening or modify the designs and retest to make sure that these sensitivities do not exist anymore. So using silicon on insulator, SOI, or silicon on sapphire radiation hardening methods would always help. So let's talk about the radiation testing for SCE, which is the basically standard method of testing the electronic circuits for SCE. And in this method, a beam of charged particle from an accelerator basically is impingent on the circuit. So you can see here this tube over here where the acceleration of the charged particle takes place. And basically there are some pros and cons for this method of the charged particle. So the pros are, first of all, they're the real particles similar to the space environment. So that is what is hitting the circuit. So we are just hitting the same particles on them, and they penetrate through metal, which is normally the case. A lot of the electronic circuits are covered by metal pieces. And you can also do absolute calibrations, measure absolute saturation cross sections and upset thresholds and error rates. So this is very useful and necessary for the satellite instruments to be tested at least once with the particle method. But on the downside, these getting an appointment for a particle accelerator could be a lengthy wait. You may need to wait a few months to get your appointment to go there. And it's also very expensive, thousands of dollars per hour. It could damage the circuit permanently, and it does not penetrate through thick layers of insulators. For example, in flip chip packaged IC, as you can see here, there's a thick layer of insulator, so the charged particle cannot penetrate through this and reach the sensitive part of the circuit. It also needs a vacuum for the measurement, because otherwise the charged particles would collide with the air molecules and lose their energy. So here's an example of a radiation facility in Finland that does the SCE testing. So you can see a very long tube where there's an electric field that is applied across this and accelerates the ions. And then the circuit is mounted inside the vacuum chamber, as you can see over here. And they create an ion cocktail, which is a mixture of 7 different types of charged particles. And this ion cocktail basically impinges on the circuit, and they do the testing. So there is a video here, so I would like to send you this video on chat. You don't have to time to watch this video, so I will send it to you on chat, and you can watch that later. Okay. So that's the standard method of testing with the radiation. All right, so once you do the testing, normally this kind of curve will be generated by the technicians who do the test or engineers who do the test, and it is the curve of cross-section versus the LET, which is a linear energy transfer. This linear energy transfer measured in mega electron volt centimeter square per milligram represents the stopping power of the material for the incoming energy. And the higher is the energy, the higher is the incoming power, the stopping power. So at some point at the beginning, the cross section is 0, but at some point it takes off, it keeps on increasing, and then by further increasing, it becomes flat. So the point where the cross section starts to rise is called the thresholdlet, and where the curve flattens off is the saturation cross section. And you need to do these, measure these to be able to calculate the error rates. So basically, it's important to determine the effective cross section and LET upset threshold. And in this example that you can see here at the bottom, you can see a beam of charged particles are impinging on the circuit, and then they create these upsets shown by the red squares. So in order to calculate the cross section, you can divide the number of upsets by the fluence of the beam, which is particles per centimeter square, the particular energy, and that will give you the value of the cross section at that energy. So that's only one point. And then you would change the energy and you generate another point, and so on until you can generate this whole curve. Now, but what about the optical method? The optical method is quite different from the radiation method in the sense that you would use a photon, you would use an optical beam to bombard the circuit. So what you would do is you would use a laser with a short picosecond pulse and picojoules or nanojoules magnitudes. You focus it using a microscope objective on the device under test. And this device under test is usually on a translation stage, and you could move around. This translation stage has a high accuracy of maybe around 1 micron or less. So you could move the beam around on different parts of the circuit and observe where the upset is occurring. You also have basically both visible and CCD and near IR cameras looking at the circuit, so you could see where your beam is, and you can also see the image of the circuit. You're illuminating the circuit with you can say both visible and near IR beams so that you can get an idea what's going on. So this way you can have several advantages. First of all, this is less expensive. It can be done everywhere, and you don't need to wait 6 months because you can just go right away, even purchase the system, bring it to your company, or even go to a place where the system is being rented out immediately. If you wanted to come tomorrow to our lab, you could do that. You don't have to wait 6 months to get there. It doesn't damage at lower energy levels. It passes through thick insulating layers. Remember we were talking about the flip chip packaged IC. It's faster and cheaper. And one great advantage of this that the particle method does not have is that it has spatial and temporal information. It could provide temporal and spatial information. And why is that? Because the beam on the particle is quite broad. So you don't have a spatial information where the beam has hit. But in case of the optical method, your beam is of the diameter of few microns. So you would know exactly at which point the upset has occurred. So, and also you have temporal information because you are using a pulse laser, so you can synchronize your event detection with the pulse and see exactly at what time this has occurred. So the temporal and spatial information are big advantages of this system. And it's also very good for commercial off-the-shelf testing. You can basically buy many pieces of commercial off-the-shelves and then test them with the laser. Basically disqualify some parts that are faulty before you take them to the accelerator. So this way you don't have to waste your time in the accelerator, spend thousands of dollars for the testing. For the parts that you already know from laser testing, it's not going to work. So what about the downside? The cons are you cannot do absolute calibration. It does not get the absolute threshold, does not penetrate through metals, and does not directly measure cross sections. So you need to calibrate against the particle method. In fact, some of the beam is reflected from the surface of the chip. So you need to have a good idea of how much reflection is there. So if you're trying to basically calibrate, you can just not get an absolute calibration. You need to make one trip to the accelerator to calibrate the whole thing. And then you can use the same curves that you generate with the laser method to know exactly what the values are. So it is basically meant to be a complementary method to the radiation testing. It's not supposed to replace the radiation testing. And that's an important point that a lot of pioneers of the field that worked in the SCE always mention in their talks. So a little bit of basic physics about the band gaps, because this is necessary to explain the SPA and TPA systems that we have, the single photon absorption, two photon absorption. So as all of you know, different materials such as metals, semiconductors, insulators, they have different band gaps. So insulator has a wide band gap, semiconductor has an average band gap, and in metals, the two bands, the conduction and the valence bands, they overlap with each other. So in case of a semiconductor, the band gap is about 1.1 electron volts, and it is possible for a photon to hit an atom in the valence band and create an electron hole pair. So electron could jump across to the valence band and contribute to the conduction. So let's see how much does that correspond to. So the 1.1 electron volt is nearly about 1100 nanometers. So if you have a laser that is operating as shorter than 1100 nanometers, it could potentially create an electron hole pair. And you can basically observe this creation of charges when you shine the laser on it. So if you do the test with the laser, You can also calculate cross-section, but your x-axis would not be LET anymore. It would be the energy per pulse in picojoules, for example. And you can see that it would generate the same type of curve as the particle test, but with a different x-axis. So there's been some attempts to correlate the two together with some theoretical formulas, but this is always more accurate and more reliable to go to a particle accelerator to do the calibration, so that you know basically how much energy picojoules corresponds to how much MeV. The shape of the curve always remains the same, so the relative values will be the same. So if you know one point is how much MeV, then you could calculate the others as well. To measure the cross section using the laser method, for example, this is one cell. So you would move the beam around within that cell, and every time you see an upset, you would reset the cell value. So if it drops from 1 to 0, you reset it back to 1, and then you would continue moving, such as this red circle is moving, and you would register how many upsets you get when you basically do a raster and cover the full area, and you'll see how many you would get. Multiply that by the area of the beam, and that would give you the cross section. So that would be at one particular laser energy. Then you would increase the energy and move on to do the raster once more. So this way you get centimeter square cross section versus the incident energy curve. Now let's talk a little bit about the penetration depth in silicon. So it turns out that longer wavelengths, they penetrate deeper into silicon. Shorter wavelengths, not that much. For example, 590 nanometer was only 1.7 micron. So it doesn't go any deeper than that. But at 1064 nanometer, 676 micron. So this has implications in case of backside illumination, which I'll talk about later. The ion beam could penetrate the metal, but it can't penetrate inside heavy insulating layers on chips. And laser pulse could penetrate these insulating layers and can reach the sensitive nodes. As long as the thickness of the insulating layer is less than the penetration depth of the beam. So if it is not, then you need to do some polishing and remove some of these insulating layers so that the beam could reach the sensitive spot. So here again, you see a curve of absorption coefficient versus wavelength, and at 1.16 micron, the absorption coefficient drops to 0. So past this, the beam is transparent, it does not get absorbed in the material. So it's quite important to note that to get the single photon absorption, we could only work below 1.16 micron and not above that. So let's talk about the single photon absorption optical excitation of carriers. And these are all described by the interaction of radiation with matter given by these three equations. And in case of single photon absorption, the energy of the photon is such that it could excite electron into the valence band and create an electron hole pair, as long as the wavelength is below 1100 nanometer. So in case of 590, it could easily do that. And when that happens, these other terms, you can see there are linear terms and the square terms. You could ignore these other terms. So only the linear terms would remain. So this is the change of intensity with distance, and this is the rate of deposition of charges. So if you consider only the first term, this would turn into a familiar Beer's absorption law, which is an exponential law, I equal to I0 e to the minus alpha z. And so you can basically see the behavior here. This is the red red parts are the deposition of charges, and this is the 1/E contour, basically where they have been deposited. So 63% of the charges have been deposited, and the intensity have been reduced to 0.336%. So in case of 800 nanometer, this penetration depth is about 7 micron, but for 590 is less than 2 micron. Also, you can say propagation of charges are in 2 dimensions, and the penetration depth increases with increasing wavelength. The penetration depth is 1/alpha, the 1/the absorption coefficient. Here again, you see the distance and 1/E point, 7 micron optical depth, 63% of the charges are deposited for the 800 nanometer at a depth of around 7 micron. Okay, so let's talk about the effect of pulse width. So what kind of pulses could we have for the laser? Could any pulse work, or how does it work? So basically, there's a very interesting paper by Douyin at IEEE Transactions, and they talk about 3 regimes of pulse width. There is 100 femtosecond to 30 picosecond in this first regime, where the threshold pulse energy is constant. So basically, this is when the pulse duration is shorter than the response time of the circuit. And then you go to the second regime, 30 picosecond to 8 nanosecond. You can see there is a rise with the pulse width in the threshold energy. And past 8 nanoseconds, there is a linear sharp rise with the increasing pulse width. So it's not that you cannot get the SCE with larger pulses, but it is preferable to have a shorter pulse of the order of maybe less than 30 picosecond, so that you get the smallest threshold pulse energy that is required. So you would trigger the SCE effect at a much smaller energy. And if you go to the larger pulses, you would need more energy to trigger the effect. So once again, talk about backside, front side illumination. As you can see in this case, the front side illumination is possible. If it is possible and is not covered by too many metal parts, you could use a shorter laser, shorter wavelength laser up to 590 nanometers. It gives you better resolution, of course, for the beam. But usually the circuits are all covered with the metal pieces, so you need to go from the back and pass through the insulating layer. And here you have to consider the penetration depths of the beam of particular wavelength. If the penetration depth is less than the thickness, then you have to shave off some of this insulation and make sure that it is quite flat, so that you get uniformity of the beam. So polishing or etching may be required for backside illumination. We also have the 2-photon absorption method. So here the beam 1260 nanometer, which is greater than 1100, is shining. And in this case, the interaction of radiation with matter equations are showing that the important components of the equations are the square, I squares, not the I. So the other terms could be all neglected. They're pretty small. And then you see the rate of the change with distance is proportional to I square, and the rate of deposition of charge is also proportional to I square. So that happens when 2 photons that have about half the band gap energy put their energies together, and then they would excite the electron from the valence band to the conduction band, produce an electron hole pair. But that does not happen at any point. That only happens when the beam is focused very, very tightly. And it also needs larger energy for the pulse. And basically, it's very localized. So I'll explain a little bit more to become more clear. So here, for example, you can see we are doing backside illumination with the 2-photon system at 1260 nanometer. So up until it's completely focused, it does not generate any electron hole pairs, such as the SPA would generate electron hole pairs along the way in an exponential way. But this one does not. It only generates it when it comes to the focus at the desired depth, which is shown by this little red rectangle there. So at this point, you also need a very short pulse, shorter than the SPA system, like about 120 femtosecond. And pulse energy should also be higher, 1 nanojoules. And when the beam is so focused, then it triggers some nonlinear effects. And then the two photons add their energies together and help the electron to jump to the electron conduction band. So you can see the SCE effect when that happens. So also you can see the generation of the charges are in 3 dimensions, and they're very, very localized. So this is a way of basically injecting the charges at one particular point. You don't have to get charges all over the place. You would only inject the charges at the point of your destination where you want it to be. And also because you can do some adjustment of the height, you could do 3D imaging as well. So you would not only could move the beam along the XY axis, you can also move it along the Z axis a little bit and then do 3D imaging. So this is the advantage of using the TPA system. So when you compare the pros and cons of TPA versus SPA, the TPA has the advantages of large penetration depths because it doesn't get absorbed so easily, and 3D imaging possible, carrier confinement in the focal zone, and it's also more similar to radiation testing because the charge track is pretty narrow, and it's very similar to what is created by the radiation testing. And backside illumination is easier. And on the downside, the TPA has lower resolution because the wavelength is larger. So a diffraction limit dictates that the beam diameter would be larger. So that reduces the resolution of the measurement, the spatial resolution of the measurement. And you also need additional components for the laser, such as the basically a parametric oscillator that you need to put there. That adds to the cost of the femtosecond laser. And because the rate of deposition is proportional to the square of the intensity, you need to make sure that your backside of the device is very homogeneous. You need to polish it very well, because otherwise the amount of charges produced will be affected in the sensitive volume. So you also have to make sure that your laser is very stable in its intensity, so it doesn't fluctuate, or these nonlinear effects will generate different amount of charges. So just to summarize, we talked about the wavelengths and single photon absorption below 1.16 and 2-photon absorption above that. Pulse duration, we talked about the 3 regimes and the 30 picosecond. There is past that, there's increase in threshold pulse energy with pulse duration. Pulse energy, we talked about for SPA, you have to use the picojoules, and for TPA, you would use nanojoules. Also, analog circuits typically require more energetic pulses than digital circuits. So typically for a digital circuit, you use picojoules, but for an op-amp, an analog circuit, you need nanojoules. And spot size is limited by diffraction limit. So if you're using longer wavelengths, your diffraction limit will go down. For our system, based on the parameters of our microscope objectives, it was about 5 micron. Our laser is at 1030 nanometer. So after doing all this theory and basics, let's try to introduce our system and a little bit about the history of the Allied Scientific Pro. So this is the first commercial system that we sold to an aerospace company in the US in 2015. It was a SPA system with the potential to be upgraded to TPA. And you can see it's a little bit bulky. So this was our first attempt to build the system. And this was sold to this aerospace company in the US. And now we have developed better systems. Our system contains 4 subsystems: the laser unit, which is a fiber laser at 1030 nanometer, and you have a whole lot of optics in front of it, the polarizers and defilters. They adjust the intensity of the beam. Basically, you can control the intensity that you want to use with some LabVIEW software. Then you have the you have the basically imaging system that has 2 cameras. Here's the imaging system over here. You have a visible CCD and a SWIR IR CCD near IR that look at the component, the device under test, which is right near the microscope objective. And the third subsystem is the illumination, which is made of an IR LED and a visible LED. IR LED at 1300 nanometer, visible at 625. So you can see both the circuits, and also you could look at the beam. Where's the beam on the circuit with the cameras? And finally, you have the translation stage and the microscope objective. So we have 2 microscope objectives, 100 times and 20 times, and our XY stage from Newport, 1 nanometer resolution. And for the vertical, we have a 30 nanometer resolution using a piezo actuator. So we have a video that I would like to share with you. Actually, this is the only video that I will run. In fact, our platform, the GoToMeeting, is not really meant for showing videos, but we can basically show this video. So I would basically play this video, and I would also share with you. So first of all, I'll share with you, and then I will play the video as well. Okay, so that's that, and let's look at this video together. Okay. So sorry about the voice. I saw the comment that you could not hear the voice, but that's why I operated basically the subtitles. And I've also sent you the presentation, so you can take a look at it again. It's a YouTube presentation, so it shouldn't be an issue. So let's move on. That was the introduction by Steve about our SPA system that could be rented here if somebody wants to come and do any testing without even purchasing the system. So here's some more information about the two systems. Our SPA has 30 picosecond pulse width and up to 3 microjoules energy per pulse, which can be, of course, attenuated using the polarizers and the ND filters, and 1030 nanometer. We also we do not have that in our SPA lab, but we could make systems, TPA systems, using basically optical parametric oscillator or amplifier that is placed in front of this 1030 nanometer, and this would act as a pump to generate wavelengths anywhere between 630 to 2600. So for TPA testing, you could operate at 1260 nanometer, for example. Your pulse width is quite short, 150 to 250, and the energies could be greater than 200 nanojoules. So if you need more information, you could email us here and get more details about the lab or the systems that we could produce. Now, for SE testing of wide bandgap semiconductors, just wanted to mention that some of the customers we have are interested on this. So you cannot use the 1030 nanometer laser. You need a different laser because these semiconductors have wider band gaps. So for gallium arsenide, 1.42 electron volts, you could use a titanium sapphire laser that could be tuned to 870 nanometer or less. Gallium nitride, you need to use an excimer laser. Its maximum laser wavelength is 364. This is the band gap wavelength. So excimer laser would do. And for silicon carbide, 2.3 electron volts, you could use a second harmonic neodymium YAG laser. So we haven't built these systems, but we are capable of building it if someone is interested in testing other type of semiconductors. So it is possible for us to do that. You cannot use the same laser. You need a different laser, that's for sure. Okay, so let us look at some of our test results. So as I said, we try to use systems that, or components that have been tested before and their results were there. And the first component that we chose was the SRAM HM6504. And this was tested by giants of the field, McMorrow, Pouget, and Buckner. They did that many years ago. So you can see here, there's one cell is enclosed in the red square, and these are the metal pieces that are shown in here. So the light would not penetrate through this. So what these guys did, they used the laser, which was about 800 nanometer, and the particular pulse energy they covered in a raster the full area of one cell. And whenever they got it upset, they reset it, and then they counted the number of upset and they measured the cross section. And then they changed the energy to a higher energy. So they start with 4 picojoules and then 7.2. And you can see the number of upset shown by the black dots are increasing. And here 10.4 picojoules more, and then 20 picojoules even more. And then eventually they could produce this curve, which is the cross section versus the laser pulse energy in picojoules. So we tried to replicate this test with our laser, which was different from their laser at 1030 nanometer. So what the first thing was to decapsulate the chip. So we got a hold of a ceramic case chip, which is easily decapsulated. So you could use a snip, side snip plier and just basically remove the cap easily. If it is a plastic cover, you need to do acid etching, and that could be quite messy. So here you can see the decapsulated chip, and these are the memory cells shown here. You also have some sense amplifiers and column decoders. These are control bits. So if you remember, I was talking about the Cepheid. If you shine the laser beam on these control bits, you may get Cepheid. But if you shine it on these bits, then you may basically, this is just one cell shown here, you get SCU. So we tried testing that. And this is our experimental setup. So we mounted the chip on an Arduino board, Arduino Uno, so we were able to write and read on it. So we wrote a 1 to all the cells, basically, initially. And this box was like a switch box that would switch between write and read, or writing a 0 or writing a 1. So instead of doing it with the software, we could just use this switch box. This is our translation stage, 1 micron resolution in the vertical direction, 30 nanometer. And this is the software. This one is LabVIEW for controlling the energy of the pulse. And this one at the bottom is the translation stage control, which was done through LabVIEW. And then the Arduino software was used to write and read. So here, for example, you can see that we were doing a read, and it just Q is the state of the cell. So all these cell numbers, they're all 1. And the two microscope objectives, the 20 times and the 100 times. The 20 times had an 8mm aperture, so it could accommodate the full beam, which had a 7mm diameter at its output. But the 100 times had only 3mm aperture, so it would block some of the beam. So the energy would be less for the 100 times, but the magnification would be more. So for the SRAM testing, we had the following settings: rep rate of 10 kilohertz for the laser. Could have been a little bit less, up to 1 kilohertz, but we used 10 kilohertz. Pulse width 30 picosecond, energy, the wavelength 10 to 30 nanometer. So we used the defocused beam, which was about 400 micron in diameter, because we wanted to test the full areas, not just one single cell. We were not doing the measurements of cross section. We just wanted to do like a checking, such as COTS parts, to just see how many cells would show upsets. So the beam diameter 400 micron, and it was much larger than the size of one cell, which is 100 by 100 micron. So there's a video here where we did this testing, which I can send you on chat. You don't have time to look at this video right now, but you could take a look at it later if you like. So it shows the full experiment live, which we did for SCE MAPLD virtual conference. So that'll be more useful to watch that. And here you can see the result. We started by using the 100 times microscope objective, and we had a 13 nanojoule pulse energy. So you may ask why the pulse energy is so large. for SCU, because this is what we wanted to see. It's because the beam is quite broad. It's about 400 micron in diameter. So if you scale it back to a 5 micron or 1 micron diameter, the energy would be of the order of picojoules. So we moved the beam represented by this circle along an inverted L shape on the device, and basically every time you move the translation stage by steps of 200 micron, and initially all the values were 1, but after illumination by the laser, some of the cells, when we did a read, some of the cells turn into 0. So you can see here, cell 719, Q equal to 1, cell 720, Q equal to 0. So that shows an upset. And here also 847, Q equal to 1, 848, Q equal to 0. That's another upset. So in total, we had 8 upsets, as you can see by these red squares in here. And we were able to write a 1 after viewing this upset. We could write a 1, no problem. Again, here we had 100 times microscope objective. We had a 60 nanojoule pulse energy in this case. So higher energy. And once we illuminated, we moved it along the L shape. Now we saw even some cells that were not even illuminated by the laser showed upset. So large areas of the chip showed upset, and it got very, very hot. So for this reason, we need to turn it off for it to cool down. And then when we turn it back on, we could write a 1 on all these upset cells. So this clearly showed the SCL because it was accompanied by heating of the chip. So it was an SCL, non-destructive SCL that we observed on this. We also tried it from initial value 0, and then some of these cells shown by red flipped to 1 when we moved the beam across this L shape. And this again was accompanied by large heat, and it required a power recycle so that we could write a 1 again. So this was again another single event latch-up. And then finally, we changed the microscope objective to 20 times, and we got a 500 nanojoules pulse energy, which was really high. And a lot of areas after moving the beam along this inverted L basically changed their state from 1 to 0, all these red ones. So more than 60–70% of the cells switched, and the chip got super hot. When we recycled the power, we could still not write a 1 on these chips that had switched state. So that clearly shows a destructive cell, because the reboot also didn't help us to fix the problem. So that was a destructive cell. And then these are some future course of action. Maybe we want to use a focus beam inside one cell, and maybe we also want to shine the beam on the control bits to get Cepheid. So these are all our future plans, but we don't have time to talk about this. I'll just go into the LM124 testing, SCT in LM124. So this one also had a ceramic chip. We had to decapsulate it, and then we mounted on a follower circuit with a picofarad probe. We investigated the output of this, and we use a digital scope. You can see the circuit is shown here. There is a Y that is tilted towards the left. You can see it over here, and this is from the literature. This is the same Y that is pointing towards the bottom. So it's the same circuit. And one of the transistors, Q9, here is quite sensitive. So we moved the beam of IR around this area, and then we looked at the scope to see what kind of basically pulses we get. There was a 260 nanojoule pulse energy at 10 kilohertz. And once we triggered the scope with the sync pulse from the laser, we observed all these pulses that are set pulses appearing across the scope. You can watch this in the video that I sent you live, or you can see it not live, but you can just watch how it just appeared run across the scope. So these are clearly set pulses. We didn't do any quantitative measurements of the dependence of the set pulse amplitude on the bias voltage, but we may do that in a future test. And finally, these are some commercial system that we built and we sold to Germany. And as you can see, this is all enclosed in a box. And this is a window that could protect against the class 4 laser. So we'd reduce the system to a class 1 laser. All the optics, this is all the basically attenuation optics. These are the laser, the controllers, the translation stage, and then we also have cameras, a visible camera and a near IR camera. So we are able to build the SPA system or SPA system with the possibility of upgrade to TPA and also a TPA system. So we come to the end of the talk, a few minutes overdue, but this is the last slide. So we saw that the SCE pulse laser system is quite useful for testing semiconductors. It's a complementary to radiation method, cannot replace it. And also optical method could demonstrate where the sensitive nodes on the circuit, and basically you can do all the cuts parts with it and identify all the error modes before you go to a radiation facility. We compared TPA with the SPA and we said what are the pros and cons of each. And TPA is of course a more expensive system than SPA. 3D mapping is possible with TPA, and you can also do backside illumination and injection at a particular depth. Optical SCE system are faster, less expensive, can be deployed at any location. And we also saw some effects, SCU, SCL in the HM6504 SRAM and SCT in the LM124 op-amp. And therefore the ASP's SCE system performance was validated. So that brings us to the end of our talk. Thank you very much for listening. And we also send you a feedback form. If you could please send your feedback, or if you have any suggestions of how to improve the webinar, I'll be glad to hear your suggestions. So at this point, if you have any questions, please feel free to either type here, or if you like, you can unmute yourself and let me know. I'll also type my email here.
Iris, I do have one question. Can you hear me?
Yes, yes, please.
Yeah, great. How hard is it to calibrate you said that it's possible to calibrate a laser beam to be, I mean, comparable to the radiation testing. How hard is it to calibrate to have the same result? And would it be possible to you have kind of predefined values and you just set them, or you need something more difficult to analyze? It depends on the device, maybe. I don't know.
Okay. So this was addressed by some of the pioneers of the field about this calibration. So let me go to the particular slide to be able to answer this. So just a second. Isolating. Yeah. So the shape of the this cross section versus pulse energy would remain the same. Okay. So if you do this with the particle accelerator, you get a shape like that, right? So you would know the relative intensity of different points, okay, where you get that cross section, right? So once you go to the accelerator, then you will get this values, but your x-axis is in LET. linear energy transfer, right? So then it would not be that difficult, because then you can see, all right, this point, which was, let's say 10% of the maximum, right? It happened at, say, 2 picojoules, and it happened at, say, 10 mega electron volts. So then you know you can calibrate. And then the relative positions would remain the same. The shape of the curve remains the same. But what I was trying to suggest is that, and also some of the pioneers of the field also emphasize that, is you cannot just use a formula. There are some formulas that you can, if you go to this paper, for example, the pulse laser testing for single event effect investigation by Buckner. Okay, so if you go to this paper, there may be some formulas that try to relate the energy in picojoules to the LET. But those formulas are not very accurate. They're not very reliable. So when you go to the pulse, you go to the particle accelerator, you get the exact values, and then you can compare that with your laser energies that you use, and then you can calibrate. Did I answer your question right?
Yes, you did. Thank you. It was a great presentation. I never actually saw much about laser testing, and now I see that is very interesting. Thank you.
Yes, especially if you want to use it for identifying the error modes that you get, right? Because your time in the accelerator is pretty limited, right? So you may stay there for a few days and you're spending thousands of dollars, right, per hour to do the test. So rather than identifying the errors there, you could use a cheaper, less expensive, more efficient, that gives you spatial resolution, temporal resolution. Identify all the errors first, and even maybe disqualify some of the components that you'll be taking to there, right? If you're testing 100 components, you could quickly disqualify some of them before you take it. So this way you reduce the amount of hours you spend in the accelerator. Does it make sense?
Yeah, it does.
Okay, great.
Thank you.
Thanks. Any other questions? Okay. If you think of other questions, I already sent you my email, rmani@alliedscientificpro.com. Feel free to send me your questions to this email. You will receive the recording of the video of this webinar. So you may want to watch it again. If there are any points that are not clear, you can ask me. Send me a email and ask. So with this, I'll come to the end of this. So I'll thank you very much for your attention.